So I'm going to show you an interesting optimization trick for iterating over numbers, skipping those that are divisible by numbers in a particular set. It doesn't have to be primes, but I like it to be primes. It just happens that I iterate over numbers and I want to avoid composites very often. So for instance, consider the primes 2, 3. So these are your basic. We're only looking at these two for now. Let's suppose you start with a number 1. This is the first number not divisible by 2 or 3. And we're just going to write down additional numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and I'll stop there. So we're going to run a sieving step. I don't have to do any fancy sieving because I can easily eliminate what's divisible by 2 and 3. 2, 3, and 4. 5 is not, 6, 7, 8, 9 is divisible by 3, 10, not 12, there you go, 13. And we're going to look at the deltas between these numbers. So 5 minus 1 is 4. We'll skip over that. 5 to 7 is 2. Now here, there are only two. I'll get to why it is, but 7 to 11 is 4. 11 to 13 is 2. I'll skip the numbers that's in between. Next one is 17. 13 to 17 is 4. 17 to 19 is 2. ... This is a repeating pattern. Now I'll tell you why it repeats. If we look at this group theoretically, let's examine the group of integers mod 2 and the group of integers mod 3 with addition. Actually, look at the rings. It doesn't even matter. So we're looking at, I'm going to put the representatives of the equivalence classes. You know, it's easier, right? 0, 1, 0, 1, 2, right? His group has order 2, his group has order 3. Now, what we're doing is, I should first make a note. Note that every positive integer, negative ones too? No, every positive integer, including 0, non-negative, we can represent as a collection, a vector of indices into these up to some given prime. So for instance, Z2 and Z3, the product of 2 and 3 is 6. I can represent every non-negative integer from 0 to 6 as a vector of indices into these groups. So for instance, the number 0 is given by 0, 0. 0 has remainder 0 when divided by 2, remainder 0 when divided by 3. Number 1 is 1, 1. It's got remainder 1 when divided by both. 2 is it might be easiest to think of this as, if you don't want to think of it as like a representation scheme for numbers, using this as your Chinese remainder trick for calculating what the number originally was, think of it as just a method of like a hashing function if you want, except it's not actually a hashing function. It's reversible as long as the number of primes you've used is large enough that you get over the original number and you can recover it. And what we're really just doing is finding our position in this. Not in this, and actually what we're actually finding our position in is Z2 x Z3, the product of the groups, which has the large order. The order is the primorial, and our position here, when we increment, it goes up. Think of it actually as a collection of wheels. What does it look like when we increment? If we're at position 0, 0 and we increment, we add 1, we end up with a number divisible by, 0 goes to 1. I'll just increment like this actually. It goes from there, then it goes 0 again, 1 goes to 2, 0 goes to 1 again, 2 goes to 0, increment one last time, 0, 1. I think I got 1, 2, 3, 4, 5. That's included already. Let's go one last time. 1, 0. Yeah, 1, 2, 3. Interesting. 1, 0. Oh, wait. Because 1 shouldn't go to 0. 1 should go to 2. And then 1 goes 0, 0. Yeah, that resets it. So 1, 2, 3, 4, 5, 6. These are the 6 numbers, 0 to 6. Represented in this scheme. And now what we're going to do is the same sieving step. Well, we're not going to do it. I'm just going to explain it. This same sieving step, if you consider that the number of numbers we're allowed to touch in these groups is the prime. The order of this group is 2. but we're removing the 0 from this group. So if we're looking at the set of things we're allowed to get to, there's only one element here. In the next one, we only have 1 and 2. If we were to add the prime 5, we would have only 1, 2, 3, and 4, and so on. So in fact, if we were to start at the beginning and iterate right across this list, skipping out the ones that touch one of these zeros, the number of things we would touch altogether is equal to something like a primorial, the product of the primes, like a factorial, but you know, primes instead, except we're subtracting 1 from each prime. So 2 minus 1 times 3 minus 1 in this case is 1 times 2, which is 2, which is the number of elements here in this repeating list. If we were to have a third prime, it's 2 minus 1 times 3 minus 1, which we know is already 2, times 5 minus 1, which is 4. So 2 4s are 8. Now I've pre-calculated the list for 3 primes. We could actually do it on paper, but I mean, I really don't feel like it. It's, what's it? 6, 4, 2, 4, 2, 4, 6, 2. If you were to start with 1, the first number not divisible by 2, 3, and 5, and I add 6, I'll get 7. Then I add 4, 8, 9, 10, 11. Add 2, 12, 13. Add 4, 15, 16, 16 17, 13, 14, 15, 16, 17. My bad. 15. I seem to think 15 comes after 13. 17 plus 2 is 19. 19 plus 4, 20, 21, 22, 23. And so on. You can tell it would obviously work. It repeats. Maybe I should, yeah, 23, 6, 79, 29, 30, 31, and then it repeats. So 31 plus 6 is 37, 38, 39, 40, 41, 42, 43, you know, on it goes forever. This is a repeating list. You will never run out. Now here's an interesting trick, and this is why I'm telling you this. Suppose you made a closure in your favorite programming language, so F, and your closure looks like this. It has internal data I equals 0, and it has this array A is equal to 6, 4, 2, 4, 2, 4, 6, 2, and we return A I plus 1. We increment at every step, mod the length of the list. And the length of the list is this that I've told you, 2, 3, 5. So I should write it L. Ln is equal to, what would be a sensible notation for this? P n, the nth prime, minus 1 times L n minus 1, and L of 1 is equal to, well, 1. Yeah, where that's the first prime. That should give you the, that should calculate this here. I mean, there's no reason to write it like that. You already see. Take the primes, subtract 1 from each, give the product. Anyway, this, I do mod L, so this is circular. That allows you to loop over it over and over. And this closure is just a function. Note in particular that this function is nothing more than an addition, this little modulus operator here, which should run in extremely, let's see, if this is divisible by, you might be able to do it with like an AND operation, get it even faster. Anyway, that's up to you to sort out. Point is, the time that this function runs in is 01. This is a constant time function, but the sum of these numbers, 6, 4, 2, 4, blah blah blah, I think the sum of those is 30, I think. So you run this function 1, 2, 3, 4, 5, 6, 7, 8 times. So after running f 8 times, you've skipped over 30 numbers, you've touched 8 of them. Or to look at it another way, were you to manually generate your numbers like this and see and remove the ones that were divisible by these primes here, to get this first 6, you would have had to test 5 numbers that came before it, show that they all failed, and then get the 6. To get this 4, you would have had to test an additional 3, they would all fail, then you get the 4. This 2, you would have had to test 1, it would have failed, you get the 2, and so on. So in this case, your speed up is equal to Maybe it'd be faster just to calculate as... That's how many numbers you do. Hold on a second while I think of the speed up. It's really funky because you got the 5 and the numbers are iffy. Oh, screw it. It's approximately equal to this primorial, what your speed up is, because you're skipping the sum numbers. Yeah, in this one case, your speed up is approximately 30x. If you were to add another prime, somewhere along the line I've been able to prove that the sum of this is equal to this for some strange reason. Can't remember why at the moment. If you were to add another prime, the next one over is 7, I think. You would have a speed up now of 7 minus 1 is 6. You get 3 6s are 18. Your speed up would be 180x. Next one is 11, which is 10. When you multiply, your speed up would be 1,800 times. This array here is so small that it fits in your cache, so that, well, I mean, the caches are enormous now. It's not when I was much younger. But anyway, sorry, I had a really crappy computer when I was smaller, and trying to learn anything that would run in decent time, like nothing would fit. Anyway, this array, assuming you're using a small number of primes, will fit in your cache, which means you have a constant time function. It's just pulling from the cache. You're not doing any fancy memory stuff. It's just an addition. Even if it was large enough that it wouldn't fit in cache, which would happen if you use more primes, you go up to 19 or so, it's still only about a megabyte. It will fit in your cache if you got an expensive processor. Well, I guess not expensive now. Maybe that's what comes off the shelf these days. But it will fit in your cache. But even if it didn't, this is just an addition and a modulus operation. Your processor's branch predictor will be able to tell what's next and pull it from memory for you. So you can essentially think of this as always pulling from cache. This is a lightning fast increment function that will skip over numbers. And I think this is, probably the best optimization you can use for, say you're looking at an integer factorization problem. You got an integer n, non-negative. You're looking at the floor of square root n. Let's call that L. Actually, I've used L before. I should call it M. Let's increment M until it lines up with 1, 1, 1, 1, 1. So M plus J is the first number which is represented as 1, 1, 1, 1, dot, 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 for however many primes you're using in this set. And we're going to call this one, we'll call it K. You have this array. This array gives you the offsets that you need to add in order to increment this number in this representation and skip over 0 anywhere. So K plus F is going to give you some funky, something like this, but it's not going to have any zeros in it. Plus F is going to give you another one. Plus F is going to give you another one. You can just repeatedly call this closure here, and it's going to skip all the stuff you don't want and be extraordinarily fast. Now here's the interesting trick. Well, another interesting trick. This can be done in parallel. Well, it's massively parallel, kinda, in that if you look at this array, it's got sum 30, it repeats. Suppose I looked at K plus the first element of the array is 6 plus 30 times n. This is a repetition of the array. So I start here, my number is represented in some form like this, all ones. I know that I have to add 6 to get to the next, what would the word be? The next element of the direct product of such and such groups. I add 30 to loop me around and get me back to exactly the same part where I was. Maybe 30 minus a little bit. It would loop you around. No, actually, because the K in the... I put the K there. K plus 30n has the same representation in this direct product of groups, no matter what. Add 6, you're always going to be the next element over in this. The other one is 4 plus 30n plus k. The next one is what? 2 plus 30n plus k. Actually, it should not be k, should it? I think you need to scan forward a little bit. Yeah, you'd have to also add 6. And you'd have to add 6 and 4. So you do an initial upfront calculation, a scan essentially, to get how much you're supposed to skip to the right of to find your spot in this. You stash it on here, then you add multiples of 30n, and each of these is striped. You run each of these in parallel. The number you can have is 1, 2, 3, 4, 8 in this case. Add more primes, you get more of them. The number you have is is enormous. It's equal to this ln. So you can only really do it with a small number of primes. Maybe go up to about 17 or so. Then you'll have millions. You can run these on millions of processors, and not a single one of them will ever encounter a number divisible by one of those primes. They'll all be pulling from their cache on what's coming next. Yeah, you stripe that as well. And then on top of that, no, there isn't anything on top of that. That's as good as it gets. Well, that's pretty damn good anyway. So not only do you get a thousands of times speed up, you can do the damn thing in parallel and get a millions of times speed up on top of it. Which is great if you're factorizing some integer and you're looking at, say, you want, in my case, what I did is I took the square root of n, I increment until I got into an element of this direct product groups, and then I look at GCD, I look at something of this form, I'm going to call it x comma n. If it shares a factor with n, this is greater than 1, and I just return that. I'm skipping over all the small primes because they're not shared with n, so I don't care about them. And in this case, my integer factorization algorithms have a millions of times speed up, which is great. The only issue is that the numbers I'm looking at are so enormous that even going millions of times faster than I should, I'm still not going to get anywhere in any reasonable amount of time. I'd have to wait hours for it to find the factor I'm looking for. Still though, nifty, useful, use it in your code.